Hello everyone. Please note that this is a NotebookLM video presentation. Thank you NotebookLM. Hope you find it useful.
So what is actually going on inside the mind of a large language model? Seriously, have you ever wondered? Well, it's not just some unknowable black box of code. It turns out there's this hidden and frankly beautiful geometry to how it organizes concepts. Today, we're going to peel back the layers and actually map out this fascinating world. And let's start with an example you've definitely seen before. You've seen this equation a million times, right? It's the classic example of word vector math, and it just feels intuitive. The relationship between king and man is pretty much the same as queen and woman. For years, this simple little analogy was the poster child for how AI gets language, but it's also the entry point into a much, much deeper mystery. Because when you really start to pull at this thread, you realize this equation isn't an answer, not really. It's the beginning of a huge question. How are concepts actually represented inside these massive neural networks? Is it all just simple arithmetic like this? That one simple idea, that concepts are basically directions in a giant high-dimensional space, is what researchers call the linear representation hypothesis. But here's the thing. What sounds simple on the surface gets complicated fast. It turns out that one phrase, concepts are represented linearly, was actually hiding several different and sometimes conflicting ideas. What's so fascinating is that when researchers really dug in, they realized linear representation was being used to mean at least three different things. First, there's the classic idea that concepts like gender are a subspace, like a shared direction in space. Second, it's about measurement, that you can use a simple linear tool called a probe to measure how likely a concept is. And third, it's about intervention, that you can actually steer the model's output, say changing a story's tense, just by adding a specific vector. And here's the puzzle. In theory, these three ideas should be different sides of the exact same coin. A steering vector for gender should be the same thing as the measurement probe for gender. But when researchers looked, using the standard Euclidean geometry we all learned in school, they just didn't line up. The math wasn't working. It was a genuine mystery, and it kind of cast doubt on the whole idea. This led to a really brilliant insight. What if the problem wasn't with the concepts themselves, but with how we were measuring the space they live in? What if we needed a different kind of geometry, a different ruler? Think about it like this. If you use a standard flat ruler on a curved map, you're going to get all the distances wrong. To do it right, you need a ruler that actually respects the curvature of the map. Well, the same principle applies here. The ruler in a vector space is a mathematical tool called an inner product, and the standard one just wasn't built for the complex, curved landscape of human language. So researchers came up with a new ruler, the causal inner product. It's designed with one simple but really powerful rule. If two concepts are causally separable, meaning you can change one without messing up the other, like changing gender without changing the language from English to French, then their vectors must be orthogonal. They have to meet at a perfect right angle. And with this new causality-aware ruler, everything just clicks into place. The puzzle vanishes. The subspace direction, the measurement probe, and the intervention vector for any given concept, they all snap into perfect alignment. They become one and the same. This was a massive step forward, unifying a whole messy set of ideas into one single, elegant theory. But solving one problem, well, it opened the door to an even bigger one. This whole framework was great for binary contrasts, male versus female, past versus present. But what about broader categories? How does an AI represent the idea of animal, or the whole category of things like mammals, birds, and fish? These aren't just simple directions anymore. They're way more complex. We had to make a leap. We were moving from a binary contrast, which is like a simple two-way street, to a categorical concept, which is more like a whole network of interconnected ideas. How does the simple geometry of lines and directions scale up to handle that kind of complexity? The crucial insight was that we needed to go from a simple direction to a true vector. And a vector doesn't just have a direction, it also has a defined length, or magnitude. You see, without a meaningful length, you can't add or subtract concepts in a way that makes any sense. So how does a concept get its length? The theory predicts something pretty remarkable. Okay, let's take a vector that represents the feature is an animal. If this representation is working perfectly, then every single animal word you can think of,
Cat, dog, tiger, you name it. When you project it onto this vector, it lands at the exact same point. The distance of that point from the center is what gives the vector its unique, meaningful length. Basically, a cat is exactly as much of an animal as a dog is.
And once every concept has a true vector, we can finally start doing real geometry. We can combine them. A whole category, like the group containing mammals, birds, and fish, is no longer just a loose collection of words. It's represented by an actual geometric shape, a polytope, formed by connecting the tips of the vectors for is mammal, is bird, and is fish.
And this is where it gets really beautiful. Because once you can represent categories as shapes, you can start to ask how related categories are organized. Specifically, what about hierarchies? The fact that a mammal is a type of animal. Let's see how this geometry actually works.
Okay, so let's build this up. First, we have the concept of animal. We now know this is represented by a specific vector with a very specific length. This is our parent concept, our base layer. Next up, we have the concept of mammal. This is also a vector, and because, well, all mammals are animals, the mammal concept is subordinate to the animal concept. Semantically, it's a subcategory, but what does it actually mean geometrically? This leads us to the key question. The concept mammal has all the information of animal baked into it, plus something extra. So how do we isolate that something extra? What is the pure essence of mammalness that distinguishes it from just the broader category of animal? It's simple vector subtraction. You take the mammal vector and you subtract the animal vector. What you have left over is a brand new vector. And that new vector represents the unique features that make something a mammal and not just any other animal. It is the geometric essence of mammalness. And here it is, the stunning conclusion. The vector representing mammalness is orthogonal to the vector representing animal. It juts out at a perfect 90-degree angle. This means the model has learned to encode the hierarchical structure of knowledge, the relationship between a category and its subcategory, as orthogonality. It's a world built on right angles. It's incredible. So we've gone from simple word math to this complex hierarchical geometry humming away inside the AI's mind. It's an absolutely incredible discovery. But so what? What can we actually do with this knowledge? Why does mapping this internal world even matter? Well, understanding this geometry gives us a real map to the model's mind. It gives us a much clearer path to interpretability. We can finally see how concepts are structured. It allows for way more precise control. Instead of just clumsy prompting, we could perform surgical interventions on the model's actual representations. And it tells us we should be building our tools totally differently, in a way that respects this natural, right-angled structure of the model's own knowledge. This discovery is really just the beginning. It suggests that deep inside these unbelievably complex models, the chaos of language and knowledge is being organized by these elegant, almost simple geometric principles. And it just forces us to ask, if the relationship between a concept and its subconcept is a right angle, what other fundamental laws of thought are just waiting to be discovered, hidden in the shapes of the AI's mind?